Hello, everybody. Hey, this is going to be our first lecture on vibrations or oscillations. So this is actually going to correspond to chapter 15 in our book. And we've already talked about the three types of motion. One was translational, one was rotational, and then this last one we're going to cover is vibrational. So vibrational or periodic motion is you can see it all over the physical world, even in your own lives. For example, if we think about how frequently do you come to this class, or how frequently do you do something? So there's going to be some regularity with this. And what we're going to use to explain this, and this is going to be specific to this chapter, is mechanical waves. Okay, so now, it's going to be mechanical waves as opposed to something like electromagnetic waves or sound waves or things like that. And we're going to use a lot of the same information that we've used in the past, for example, velocity and energy and things like that. Now, what I have here is an example here of something that is going to be periodic motion. And so what we have there is a weight on the end of a spring, okay? The weight on the end of the spring, and we can see there that this is going to be going up and down. All right, so it is going to have a frequency, it is going to have a period. Okay, so first of all, let's talk about simple harmonic motion. Now, simple harmonic motion is very often abbreviated with SHM, or a simple harmonic oscillator, which would be simple harmonic oscillator. I suppose it's the difference between a noun and an adjective. Okay, now we can see that this spring has slowed down. But what is interesting about this, as this goes up and down, it's kept the same period. It is kept the same time. Okay, so we're going to come back to that. But we need a sort of a definition of simple harmonic motion. And you can look up a lot of these things, but a simple harmonic motion, a mass will exhibit simple harmonic motion when a restoring force is proportional to the displacement from the equilibrium position. All right, so let's kind of talk about that. So just a mass will exhibit simple harmonic motion if the restoring force is proportional to the displacement from the equilibrium. Okay, so now as we look at this as this oscillator, as this slowing down, it's essentially going to come to rest. Okay, and I'm going to try to get this perspective. So it's going to be, so from this view, this is what I'm going to call X naught. Okay. X naught is the okay, so that is the equilibrium position. Okay, so from that view, now what we can do is we can stretch that down, okay, or we can push it up. Okay, and if we push it up and let it go, now it's going to oscillate. It's going to oscillate back and forth on either side of the equilibrium position. So when we think about the restoring force, as it comes down, right? As it comes down, the spring is pulling it back. So that spring is the restoring force, and it's acting in the opposite direction. It's acting in the opposite direction of displacement. Same thing happens up here. When we push it up here, the spring is pushing down as well as gravity, okay? And we're going to come to an example where we don't have to worry about the combination of the spring and gravity in there, because it adds a little complexity there. But if I pull it down, let's say this far, we would have an amplitude, okay? So if I bring it down there, okay, now it's going to go up, and we're going to have an amplitude that is going to be something like there, okay? So it's trying to get this to go straight up and down. Okay. All right, so this might need to be a little bit lower. Okay. So anyways, we can see that it is going to go back and forth. We can see that it's going to go back and forth. So this A here, and this would be, if we say up is positive, then this would be the positive amplitude. So A is the amplitude of the wave, which would be equal to the maximum displacement. Okay, and a couple other definitions here, and that would be period, okay, capital T, period, would equal the time for one cycle. Okay, it is the time for one cycle. Now, you guys might also think of this, the period, as the time for one revolution, okay? Which, strictly speaking, is not correct for this, because this is going up and down. It's not going in a circle, but we're going to see the similarities between something that's going in a circle and something that's going up and down. So there's going to be a lot of similarities to rotational motion, even though technically they're not going to be the same. Okay, and we have frequency, which is the number of cycles per time. Okay, and if you think about this, you might remember this from math classes. Period is going to equal to 1 over frequency, and vice versa. So here's the time. Period is the time for one revolution, and frequency would be the number of cycles per time. Okay, cycles per, let's say, seconds. So the units for period is the standard units would be seconds. It could be minutes or hours, whatever. The standard units for frequency. Okay, so period unit, we'll say seconds. Frequency unit is going to be the inverse of seconds, which would be seconds to the -1. And you might also remember that would be measured in hertz. Okay, now I have a drawing here that is going to kind of show us this vibration, but we're going to visualize this. We're going to visualize this as something that is going left and right on a frictionless surface. So we'll say the coefficient of friction is 0. And so now we're going to think about pulling this mass this way. And now there's a restoring force. There's a restoring force that's taking it back to the left. And as it goes through the equilibrium position, its momentum is carrying it through. And now as it goes through this way, the spring is pushing back against it. Okay, so eventually it's going to slow down. So now the restoring force is going to be again, proportional to the displacement from the equilibrium position. So the equilibrium position, or x, okay, so we're going to go here would be negative x, and this direction would be positive x. And remember that a and negative a would be the maximum or minimum displacement. Okay, so down here in this last one, we could see that if we were continuing here, this mass would then be pushing back. Okay, but remember, in a different cycle there, this could be coming in the other direction, right? Okay, so this could have been this intermediate spot in there. So this is what I would like you guys to sort of visualize in your head as we talk about the next sort of section here. All right. So now we're going to go back to something we had second quarter, which is called Hooke's law. And you might remember that is for a spring, and the force of a spring is going to equal to negative kx, and this was called the spring constant. And we know x is going to be displacement. So this negative here is essentially indicating that the force is always in the opposite direction. The force is always in the opposite direction of displacement, which is key to think about in simple harmonic motion, because we said the restoring force is always in the opposite direction of displacement. So we kind of have this thing sort of set up. Okay. Now, if we want to translate this into acceleration, okay, now remember, force is equal to ma. So now we can say acceleration is equal to negative kmx, negative kx. And this, when you read into the first couple sections of chapter 15, this might seem a little bit odd, but what we're going to sort of assume here is that omega squared is equal to k over m. Okay, so this omega is called the angular frequency. The angular frequency. Now, in the chapter that we covered just a little bit ago, this was the angular velocity. Okay, so angular frequency is not the same thing as angular velocity, but as I mentioned before, the circular motion and the vibrational motion are going to have many similar things. So although technically it's not the same, from a practical matter of understanding it, they are the same, and I will show you a nice example in my next lecture as to why that is. Okay, so what we're going to do here is realize that acceleration, okay, acceleration is going to be the second derivative. The second derivative of position with respect to time. The second derivative with respect to time. And so essentially what we are looking at here, if we're looking for a function, if we're looking for a function of position, we're looking for a function of position. So now remember, if we integrate acceleration twice, then we would get to position. Or if we were at position and we took the differential twice, then we would end up with acceleration. So we're going to kind of do that now. What we want to end up with, is a function that after we either differentiate it twice or integrate it twice, we're going to have the same function, except it's going to be negative. It's going to be the same function but negative. And as it turns out, we're going to have a cosine or sine curve. Okay, and it is really known as a sinoidal curve because the difference between a sine and a cosine is essentially just where we start. And I am going to show you a picture of that, and we'll talk about it. So as it turns out. So we're going to say the position, wherever the position is, and that is equal to A cosine omega t plus phi. Okay, X is the position, A is the maximum position, which would be amplitude, times the cosine of omega t plus phi. Now, this right here is again the angular frequency. This is called the phase constant. And we can kind of ignore this for now, and I'll show you here in a second with another diagram of what that would be. Now, again, if we differentiate this position with respect to time, we're going to get velocity. And so our velocity is going to be, using the chain rule, is we're going to have omega A sine omega t plus phi, okay? And that is going to be negative, okay? And then if we want acceleration, we're going to have negative omega squared A cosine omega t plus phi. All right, so this is going to satisfy our needs here because the second differential of position is going to be acceleration, and we want that for simple harmonic motion is to be the same function, which is cosine and cosine of omega t plus phi, except that it's going to be negative. Okay, so these are going to be three equations, essentially our kinematic equations of determining the position, the velocity, and the acceleration. So we're definitely going to use this, and we'll talk more about this as we go. Now, if we think about these three, we're going to think about these three, and I'm going to show you another. Sort of diagram here, which will illustrate the validity of these equations and hopefully give you guys a better understanding of what's going on. All right. So here we have, okay, and let me see if we can get this. All right, so what I've got here in black is going to be the position function, okay? So I'm arbitrarily saying that our mass is going to start out at its maximum amplitude. If you think back to that diagram that I made with the spring, I pulled it all the way to the positive A, okay? So now, as it moves, all right, it's going to have the maximum acceleration there. It's going to have the maximum acceleration because the spring is pushed in the most. Remember, acceleration is going to be proportional to the amount of spring is compressed, okay? So maximum acceleration. But now, as the spring moves forward, okay, there becomes progressively less and less force, until it reaches the equilibrium position. But at the same time, even though it had the maximum acceleration, the velocity started out at 0. Okay, so we're going to have that sort of maximum amount of acceleration there, but it's going to start off more slowly, and this acceleration, okay, is going to diminish, but the velocity is still going to go up. And so once we reach the equilibrium position, okay, we can see that the acceleration is going to be the maximum, or at least the absolute value. The absolute value is going to be the maximum. So we could really think about that as the minimum. Okay, so now it's going to come down to the other side, which is going to reach the negative amplitude. Okay, and it's going to go back up, and it's going to continue to go. And we can see that with, just imagine the spring that I had, it kept going and going and going. Now, in this case, we are ignoring friction, Okay, so the amplitude is not going to diminish, where in my original example, we saw that that magnitude slowly kind of came to a stop. And so the magnitude kind of diminished over time. So this obviously is our ideal, All right, so now we take the differential of position, and that's going to give us our velocity. So now remember, the differential is just the equation for the tangent, So we can see right here that up here, if we took the tangent there, that the slope of that tangent is going to be equal to 0. So our velocity, which is going to be in purple, starts out at 0. Our velocity starts out at purple. Now, if we are talking about the spring, we're saying down is negative. If we're talking about the spring going left and right, we said to the right was positive and now it's going this way. So it's going in the negative direction. So that means it's going to have a negative velocity. Okay, so it's going to experience this force, this acceleration that's going to make it go faster and faster and faster. But we can see that that force, that acceleration is diminishing over time, so it's going to flatten out. And so once we get here at the bottom, this is where the spring is in the middle. That means it's neither compressed nor stretched. So there is no force, and that's what is meant by the equilibrium position, okay? No force in either direction. So its momentum is going to carry it forward, right? So we're still going to have a change in velocity, but momentarily this acceleration is going to be 0, okay? But that's also going to be the absolute value of that velocity is going to be the max, okay? Just happens to be the maximum in the negative direction, which can be a little confusing because technically that would be the minimum velocity because it's in the negative direction. All right, so now it's going to come back up. And so when we get this oscillator, the mass, when it reaches the other amplitude, in this case the negative amplitude, we can see that the velocity is going to be 0. So that purple is going to be 0. And that makes sense because as it's oscillating back and forth, when it gets to the amplitude, it's going to reach that temporary, momentary stoppage, right? So it's going in one direction and then it's going to turn around and go the other way. So there's got to be a time, just an instant, where it has stopped. And that's going to correspond to there, okay? So, and that's, again, going to continue. That is going to continue on. All right. So if we think about now the acceleration, we already talked about the acceleration being the max there because that's where the spring, is at its maximum compression or stretch, okay? Now in our case, that would be a stretch, but if we pulled the spring this way, okay, now remember that would be maximum displacement in the positive direction, but the restoring force is always going in the opposite direction. So this would be a maximum absolute value of the maximum acceleration. So technically it's a deceleration because it's going in the opposite direction. So now we can see here that our green here is going to be our acceleration function, okay? And for kind of those same purposes, it's going to go up and down here. So we can see that if we start up here, this is a cosine curve, okay? Regular cosine curve, okay? And we can see that the purple is going to be a negative sine curve. And we can see the acceleration is a negative cosine curve. Now, this right here is corresponding to now our 3 basic equations for position, velocity, and acceleration. And this is in accordance to a simple harmonic oscillator or simple harmonic motion, because in simple harmonic motion, we're going to have a restoring force that is proportional to the displacement. All right, so in our next lecture, we're going to explore more of this. We're going to take a look at experimental values of our spring here, and we will measure the frequency and the period, etc. Okay, we will see you next time.